In this part, we study the Stokes formula. For Stokes formula, we need a surface which boundary. Uh, to study surface which boundary, we need to extend our differentiability of maps. Actually, we studied this when we studied differential calculus before, but we just record this here. D is a subset of Rn, not necessarily open. And a map F defined on D to another Euclidean space Rm, we said that this map is Ck. If there is an open set, there are open sets. O containing D, and another map F bar defined on O such that F bar X equal Fx for X in D. So this is our D. Might not be opened, but if you can find a larger open set O containing D such that, and also a map F bar from O to Rm such that the restriction of F bar on D is precisely our F. That is, for every point in D, F bar X equal Fx. F only defined on D. Outside of D, for example, if the point is here, F bar has definition. F bar is defined here, but F is not. But for point in D, both F and F bar make sense. Then if they are equal, if this map is Ck, if the F bar is Ck, then we say that F is Ck as a map defined on D. Okay. So I just want to say, using this, I just want to say continuously differentiable is also applied to map defined on no open set. Even if the domain of definition is not an open set, it makes sense to say that the map is Ck or is continuously differentiable. Okay. Now, a parametric surface which boundary surface S which boundary, maybe no, not S. Parametric surface which boundary is a map, is an injective C2 map. C2 is not necessary, sometimes C1 is enough. This map is defined on D, two-dimensional D, to R3. Which this map, the derivative is bounded, which bounded derivative. Okay. Here what's D? D is a closed Jordan domain. Which piecewise smooth boundary. Okay. The boundary is D. Okay, so we have a parametric surface which boundary. The difference with the previous parametric surface is that the domain of definition of R is not a region anymore. Region is open Jordan domain. Now our D is closed, therefore we have boundary. Okay, and the boundary is piecewise smooth. Okay, so the image of such parametric surface with boundary is the surface with boundary. Is surface with boundary. The boundary is denoted by pencil D. Sorry, boundary not this. Boundary is S. This is the image of the boundary of D. Okay, so this is the basic definition to state the Stokes formula. For example, the hemisphere, the graph of this function is a surface which boundary. The boundary is the unit circle in xy plane. Okay, the picture is here. This is the hemisphere, that is the graph of this z function. So the boundary is the unit circle in the xy plane. Okay, but if you change the domain of definition by x squared plus y squared less than 1, then this is not a surface with boundary. This is simply a surface without boundary. Okay. Next, we consider the orientation of surface with boundary. So, as before, we use this to say that S is a surface with parametrization, the map R, and this is for surface with boundary. We also use the same notation. S is a surface with boundary. So S has a normal vector. So this is S. We have normal vector. The normal vector is determined by the partial derivative. But we use the unit normal vector. So this surface can be oriented by n equal RU cross RV normalized divided by its norm. At every point, you have two unit normal vector which reverse direction. Choose any one of them, give you an orientation of the surface. Okay, you can also use this orientation. This is RV cross RU. Switch the order of UV, reverse the vector. Okay, so choosing an order of UV, given a parametrization, choosing an order of the UV give you an orientation. So how about the boundary of the surface, the orientation of the boundary? We want to determine the orientation of the boundary. That is, so this surface is the image of R from D in the UV plane. Okay. Now the boundary, if we have a parametrization phi, if phi, suppose phi from an interval AB to R2 is a parametrization of the boundary curve of the D. That is, we have a phi here is AB domain, AB interval. So this phi is the parametrization of the boundary of D. This suppose phi induced the positive orientation, which induced the positive orientation of the boundary. That is the derivative, the tangent vector is positive to the boundary. That is, you go along when t increase, the point phi t move along the boundary of D, and move in the direction so that when you move, D is on your left side. So such phi is called induce a positive orientation. Okay, so for such a phi, the composition of phi under the map R give you a map from AB to the boundary of S. That is gamma. Then gamma be the composition of R and the phi, which is a map from the interval to R3. This is a parametrization of the boundary of S. Because S is the, because for t in AB, phi t in boundary of D, then gamma t, that is R, phi t in the R boundary, that is the boundary of S. So this map is, the image of this map is the boundary of S. Actually, it is the parametrization of the boundary curve of the boundary of our surface Vichy boundary. Okay. So the orientation induced by this map, that is the tangent vector, given a curve, given a patch, the orientation is determined by the tangent vector or by the increasement of t. When t increase, where the point gamma t move, the direction of the point gamma t move, that is the tangent vector, give you an orientation of the curve of the patch. So this parametrization determine the orientation determined by this gamma, by this parametrization of the boundary curve, boundary patch, is called the induced orientation on the boundary curve. That is given an orientation on the of the surface, that is given a vector n, a normal vector n, a normal vector on S, determine an orientation. You automatically have an orientation on the boundary curve. That is determined in this manner by choosing a parametrization of S, that is the map R, so that the induced the generalized normal vector coincide with your orientation on S. That is, this n is precisely the unit normal vector of S. Then with this parametrization R, you choose a parametrization of the boundary of D, that is our phi. Then you construct using phi and R you construct this map. You construct this, which is a parametrization of the boundary of S. This parametrization automatically gives you an orientation of the boundary. So this boundary is determined. This orientation is of the boundary curve S is determined by the chosen of n, whether you take this as n or the reverse direction. Okay. If you reverse the direction, the orientation of the boundary also reverse. Okay. Now we have a look on an example. Suppose S is this xy, gxy, xy belongs to D. That is, S is a graph of a function. Here is D, x, y, z, and S is this is S. Then we can take a parametrization of S by R, D to the R3, Rxy is xy, gxy. Okay, so we have an R. Then this vector Rx cross Ry normalized. This vector is minus partial derivative of g, partial derivative of then 1. This we have computed previously. So this is an upper pointed outward. So this vector is that is if we choose the upper side of S as orientation, that is the normal vector is pointed upward. Then our parametrization are given here coincide with the orientation of S. Because the normal vector determined by this parametrization also point upward because the third component is positive. So if you take the orientation on D to be positive, in the sense of green formula, that is when you go around the boundary of D, D is on your left side. Then correspondingly, the induced orientation on the boundary of S is just this direction. That is lifting the orientation of D to S. Okay. In other words, if you suppose you given an orientation on the boundary of S, then projecting it to xy plane, which is just the positive orientation of the boundary of D, then the orientation on S is precisely the induced orientation. Induced is the orientation induced by the upward. That is, if you oriented S upward, then the corresponding orientation on the boundary of S, the projection of that orientation is the positive orientation of the boundary of D. Okay, so this is the orientation. That is, if you use your right hand, which your thumb pointed upward, then the other forefinger, the rotation direction of the other forefinger is precisely the orientation of S, of the boundary of S. Okay. So this is the surface ridge boundary and the induced boundary of the boundary curve. We introduced this concept briefly.